Okay, hello everybody. So let us revise mole concept and redox reactions. Mole concept as well as redox reactions are important topics of physical chemistry, and we must be very thorough with both of them. So before starting with questions, let's look at some basic formulae which we use again and again. So all of you are thorough with this formula, number of moles. So what is the fundamental formula for number of moles? It is weight in grams of a substance upon molar mass of the substance. Which means if I know the number of moles and the molar mass of a substance, I can find out the weight in grams by multiplying molar mass and number of moles. Which means in this formula, if one particular quantity is unknown and the remaining two unknown, we can use the formula and get the value of the unknown parameter. Okay, the point to be noted here is that it's grams. So if weight is given in kilograms or milligrams, kindly convert it to grams and then we can use this formula. So that is one thing. Another very important formula for number of moles is this. Number of moles is equal to molarity. So I'm writing in a little different way. You are used to seeing the formula in this manner. Molarity is equal to number of moles of solute upon liters of solution. So I'm writing it in a little different way because I want number of moles to appear on the left hand side. So I'm writing in this way. Number of moles is equal to molarity multiplied by the volume of the solution in liters. So again you have to take care of the units. Liters of solution. If the value of volume is given in ml, we must convert ml to liters. So if I want to convert from ml to L, that is from milliliters to liters, I have to divide by 1000 and then I can use this formula. So please remember that both these formula are equally important. Don't ignore any of them. Both are extremely important, and also in some cases we are required to use both the formula in the same sum. So in the same question both of these will be used depending on the data given. Okay, so quick recap of number of moles and take care of the units. Here it's liters of solution. All right, now if I look at one more formula, now this particular formula is applicable only and only at STP or NTP. So number of moles, and yes, for gases of course. See, these two formula, the first and second formula, are used everywhere. We can use them for solids, we can use them for liquids, we can use them for gases, I mean whatever is present. But the third one, that is when we are talking about STP, we are talking specifically about a gas. So number of moles of gas. Okay. Number of moles of gas is equal to the volume in liters at STP upon 22.4. So if they are talking about STP or NTP, then we can use this formula. And again, this is always applicable irrespective of whether the substance is at STP or not. But the third formula is applicable if the gas is present at STP. Again, here it's liters, not milliliters, right? Okay. 1 liter is equal to 1000 ml, also called 1000 cc. cc is centimeter cube, ml is also called cc, and liter is also called dm cube. So you are more used to liters, but then dm cube also means the same. So liter and dm cube can be used for the to denote the same thing. So don't get confused. Dm cube is decimeter cube, cc is centimeter cube, and sometimes this cc is written like this: cc, centimeter cube, right? Okay. Another important conversion is this. So you should know all of these. Fine. Now, let's come to the next important formula. Number of GEQ. Now, GEQ is called gram equivalence. GEQ is called gram equivalence. GEQ, we can write like this. Don't have to write the full thing, but you should know that GEQ means gram equivalence. So, number of GEQ is equal to number of moles multiplied by NF. NF is N factor. Number of GQ is equal to number of moles into N factor. Now, N factor is something which you have to be careful about, because if it's a redox reaction, then we should know how to find out N factor of the oxidizing agent, N factor of the reducing agent. And if it is not a redox reaction, if it's a simple acid-base reaction, that is a reaction occurring between an acid and a base, then also you should know how to find out the N factor of the acid, N factor of the base. Okay. Now, another important thing is 1 GEQ is equal to 1000 MEQ. MEQ means milli equivalent. So 1 GEQ is equal to 1000 MEQ. 1 gram equivalent is equal to 1000 milli equivalents. Similarly, we know that 1 mole is equal to 1000 millimoles. 1 mole is equal to 1000 millimoles. This is millimoles, mmol. And MEQ is milliequivalent. So we must be thorough with these parameters. Okay. Let's do some more formulae. Molality. Molality is equal to number of moles of solute upon kilograms of solvent. Now, here the mass of solvent is in kilograms, so we are not supposed to take grams or any other unit. So be careful. Another point to be taken care of is that here it is solvent and not solution. It is solvent. So this is molality. Another important concentration term is normality. So this is the formula of normality. Look at the formula of normality and also look at this, that is molarity. If you compare this with this, you will realize that the numerator is different but the denominator is same. Because if we look at the formula of molarity, molarity is what? Number of moles of solute. In the numerator we have number of moles of solute. and in the denominator we have liters of solution. All right, so compare these two. Clearly it is visible that the numerators are different but the denominator is same for both, right? So these are some basic concentration terms: molarity, molality, normality, which we use again and again to solve questions. We use these to solve questions which are asked on mole concept, questions which are asked from redox, and also there are so many other chapters in physical chemistry in which we use these concentration terms, right? So you must be thorough with these formulae. Okay, now another important term is mole fraction. See, if I have a mixture, let's say I have two or more than two components, and I'm interested in finding out the mole fraction of a particular component, then I should write like this: number of moles of that component upon sum of moles of all components. Fraction means it has to be less than 1, right? So the numerator has to be smaller than the denominator. Obviously, isn't it common sense? Sum of moles of all components. You are adding the moles of all the components in the mixture. So definitely the denominator is going to be higher in value as compared to the numerator. In the numerator, you take moles of only that specific substance whose mole fraction we are interested in finding. Now, mole percentage also is quite common. So it's nothing but mole fraction into 100. So mole percentage is mole fraction into 100. What is mass fraction? Replace the word mole with mass. So here, instead of writing moles, I can write grams of that component. That component means I'm talking about a particular component which is present in the mixture. So if there are two components A and B, and if I want to find out the mass fraction of A, then in the numerator I should write grams of A. So grams of the component. Grams of that component upon total mass of the mixture, or we can say sum of grams of all components. Right? And mass percentage will be mass fraction into 100. Alright. Again, mass fraction has to be less than 1 because anything which contains the word fraction has to be less than 1 because the numerator is smaller than the denominator. Alright. So these are some basic things. Now see, this is quite common. You come across this in questions. Now what does this mean? This means molarity is 0.1. I can also write like this, right? Likewise, m upon 100 would be molarity is 0.01. N by 10 would mean normality is 0.1. and so on. Okay. Sometimes people get confused looking at these. So these are common. So don't get confused. This is also called decimolar. Means if I come across a sentence of this sort, a decimolar solution, that means the molarity of the solution is 0.1 moles per liter. Similarly, decinormal, this would mean decinormal. All right. So these are common. Units are extremely important. While applying a formula, take care of the units. Check whether you have the required parameters in the units which are appropriate. So appropriate units are required. If you go wrong while applying the unit, the entire answer will be wrong. So be careful. Even if you know the correct formula, just because you have not used the correct unit, you will end up getting a wrong answer. That should not happen. Okay, coming back to that concept of n factor. N factor. Remember, we were talking about n factor when we were discussing GQ and normality. So n factor is what? N factor is basicity of the acid if it is an acid-base reaction. So if we are talking about the n factor of an acid in an acid-base reaction, we will say that n factor of the acid is basicity of the acid. So n factor will be basicity of acid if the substance is behaving as an acid in the reaction. Similarly, for a base, we will say n factor is the acidity of the base. But if it is a redox reaction, we must find out the oxidation states and then eventually we'll be able to determine the NF values. So we will look at those things after some time. But as of now, you should know that if it's an acid-base reaction, then NF of the acid is basicity of the acid, NF of base is acidity of base. Let's start with some questions. See, physical chemistry can be mastered only if you solve more and more questions. Because sometimes you make silly mistakes even if you apply the correct formula. So it is better to keep practicing. So keep solving as many questions as possible. Okay, let's start. The first question is of this kind. Which contains least number of molecules? Very, very easy question and also very important. This type is very common for NEET. Least number of molecules, maximum number of molecules, maximum number of atoms, least number of atoms. Such questions are common. Okay, so which contains least number of molecules? We have 4 options. Now see, least number of molecules, that means we should find out the number of molecules. Number of molecules for this, 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 and then we'll compare. How do we find out number of molecules? Number of molecules is equal to number of moles multiplied by Avogadro's number. So, for the first one, what is the number of moles in 1 gram of CO2? We have discussed the formula. 1 gram of CO2 means 1 upon 44 moles, because moles is grams by molar mass. Molar mass of CO2 will be 44 grams per mole. So 1 by 44 is the number of moles of CO2. If I multiply this by Na, that is Avogadro's number, this will give me the exact number of molecules. Of course, I have to put the value here, 6.022 into 10 raised to 23, and then I'll get the exact number of molecules. But I'm not interested in finding out the exact number of molecules now, because I just need to compare the values here. So I'll just keep Na as Na. Okay, for the next one, 1 upon 28 into Na. This will be the number of molecules in 1 gram of N2. Molar mass of N2 is 28 gram per mole. Atomic mass of nitrogen is 14, and hence we get 28 gram per mole as a molar mass. Likewise for oxygen. Oxygen is also diatomic. So atomic mass of oxygen is 16. So the molar mass of O2 molecule will be 32 gram per mole. 1 upon 32 this is the number of moles. Number of moles into Na is the number of molecules. Moles into Na is number of molecules. For this one, for hydrogen, so 1 upon 2 into. Now see, there is a common tendency. Whenever you see hydrogen, you put mass as 1, that is the molar mass, but that is not correct. Molar mass of H2 is 2 gram per mole. Atomic mass of hydrogen is 1, so molar mass of H2 will be 2 gram per mole. Okay. So number of molecules for every option I have written here. Least number of molecules. So which value is the least? Now see, the numerator is same for all. The numerator is same for all. So we don't need to look at the numerator. Let's look at the denominators. We know that in mathematics we have learned that if numerators are same, but if the denominators are different, then just compare the denominators. So let's look at these denominators. Now least number of molecules. So we want the lowest value out of these. Lowest value would mean highest value of denominator because the numerators are same. Highest value of denominator is here. 44, 28, 32, 2. So these are the denominators. The highest value is 44. Denominator is highest here, which means this value will be the lowest. So least number of molecules. So option A is the correct option. Next question. If VML of the vapors of a substance at NTP, see, even if it is NTP, we can use the formula that we discussed for STP. So for STP and NTP, we will use the same formula, and we have already discussed that it is applicable for a gas. Alright, so VML of the vapors, that means the volume of the gas at NTP is VML. They have specified the unit, which means I need to convert it to liters. So I'll say that the volume is V upon 1000 liters. Units are extremely important. Right? Okay. Now, number of moles. Number of moles is equal to volume in liters at STP upon 22.4. So let's use that. Right? Alright. So this is what I'll get. Now, on solving this, I'll get 22400. This is the number of moles. V upon 22400. Right? Now, we already know that for any substance, number of moles is weight in grams upon molar mass. So, W gram is the weight. So, this is equal to grams upon molar mass. Let M be the molar mass of the substance. Now, molecular weight. We know molecular weight and molar mass both have the same value but different units. So, I'll get the same value here, which means if I cross multiply, I'll get the value of M. Therefore, M will be equal to 22400 W upon V. This is the value of molar mass, and we know that for molar mass the unit is gram per mole, and for molecular mass the unit is U, right, small u. So this is the value of molecular mass in U, 22400 W by V. How did I get this? I cross multiplied. M into V is equal to W into 22400. M is the molar mass. This is what grams by molar mass. This is what volume in liters at STP upon 22.4. So which is the option? So if I look at this, it is the first one, W by V into 2240. Yes. Next question. A hydrocarbon contains 80% of carbon. What is the hydrocarbon? Okay. Now see, hydrocarbon itself means only carbon and hydrogen atoms are present. There is no oxygen, there is no nitrogen, there is no other element. A hydrocarbon will consist of carbon and hydrogen only. Hence, it's a hydrocarbon. So, they have mentioned that 80% of carbon, which means if I find out the mass percentage of carbon in the hydrocarbon, right? I have 4 different options with me. So, for every option, if I find out the percentage of carbon, then only I will be able to comment. So, percentage of carbon, mass percentage of carbon. See, they have not mentioned the word mass. It's understood if nothing is mentioned that they're talking about the mass percent or weight percent of carbon within that hydrocarbon. So, mass percentage of carbon in CH4. So, how do you find out mass percentage of carbon in CH4? Very simple. Look at the formula, right? In the denominator, simply put molar mass of the entire substance. So 16 gram per mole is the molar mass. And then look at carbon. So carbon, so here you have 1. If nothing is written, it means 1 is written. So 1, multiply that number with atomic mass of the element which is being considered. So here carbon is being considered, and hence I can say that this is the mass percentage of carbon in CH4, right? That means the mass percentage of carbon in methane is 75%. So methane is not the desired hydrocarbon because clearly it is mentioned that 80% of carbon must be present. 80% of carbon must be present. In this way we can check for every option. Let's check randomly option C, and then we can get a rough idea, or we can get the complete idea if C is our answer. So let's see. For example, if I get 80 as the answer for C, I will not check B, I will not check D because only one option is correct here. So percentage of carbon in C2H6. So denominator 2 into 12 plus 6 into 1, that is 30. Molar mass is 30, and then we're talking about carbon, so 2 into 12 and then into 100, right? Yes, we got 80 here, so need not check the other options. 20 into 4 is 80, and hence the hydrocarbon is C2H6, which is ethane. So IUPAC name of C2H6 is ethane. Next question. The simplest formula. Now, whenever you look at this means they are talking about the empirical formula. Empirical formula. Simplest formula means empirical formula. So we have to determine the empirical formula of the compound. Okay, the compound contains 2 elements X and Y. Clearly they have mentioned, you can check the options. And this means atomic weight. ATWT is atomic weight or atomic mass, and 50% of element X and 50%. See, if there are 2 elements and the percentage composition of one element is 50, obviously the percentage composition of the other element will also be 50, right? Because there are only 2 elements. So 100 minus 50 is 50. So we know the mass percentage of each element within the compound. Now, mass percentage of each element is 50. So what is the traditional method of finding out empirical formula? We write the mass percentages of the elements, X and Y. These are the 2 elements, right? I'm making columns. That same old procedure I'm following. Because there are only 2 elements, we can follow the same old procedure. Okay. So 50 is the mass percentage of X. What is the atomic weight of X? Atomic weight of X is 10. Right? Then atomic weight of Y is 20. Right? Which means if I take the simplest ratio, it is 5 is to 2.5. 5 is to 2.5 is 2 is to 1. So this is the correct empirical formula. B is the correct answer. Next. Okay, very interesting question. So now we have stoichiometry with us. We have a reaction. Although it's an easy reaction, but the concept is extremely important because we will talk about limiting reagent. Limiting reagent, LR. You all are familiar with LR. So the full form is limiting reagent or limiting reactant also we can say. Now, these are the two reactants and C is the product. Now see, already the reaction is balanced because you can see the coefficient here 2 has been already put in front of B, so the reaction has already been balanced, so we need not balance it. Okay, now 5 moles of A and 8 moles of B will produce how many moles of C? This is the question. They want to know the number of moles of C formed. Number of moles of C formed. So C is the product. Now going back to stoichiometry, we all know that if we are dealing with a particular chemical reaction, we must balance that chemical reaction and then proceed. Already it has been balanced. Alright, let's look at the coefficients. Coefficient of A is 1, coefficient of B is 2, coefficient of C is 1. Okay. Now, if we read this question carefully, clearly it is mentioned that 5 moles of A had been taken and 8 moles of B had been taken, which means the quantities of both the reactants have been specified in the question. The quantities of both the reactants, not one reactant, the quantities of both the reactants have been specified in the question. If quantities of both the reactants are mentioned in the question, then we must determine the limiting reagent. So, we don't know which is the limiting reagent. A could be a limiting reagent, B could be a limiting reagent. So, let's find out who the limiting reagent is. Now, see. How do you find out who the limiting reagent is? There is an easy technique for that. The technique is this. Make a small box. Okay. It doesn't look so small, but anyway. Within that box, I'll write the necessary details required for finding out the limiting reagent. Now, for A, I have been given 5 moles of A initially. In the question, whatever they have mentioned, that is initial quantity, because we had started with 5 moles of A and 8 moles of B. We don't know how much of A has reacted, how much of B has reacted. All those things need to be found out. Right. 5 moles of A. And for B, it is 8. One more thing. We need moles, not grams. So let's say we have a situation wherein grams of reactants are given. Then we must convert the grams to moles and then proceed with this, because we need moles and not grams. Whenever we are dealing with stoichiometry, we must focus on moles, not on grams. Okay, now the technique I'll explain here. Very easy technique it is. You write the number of moles. So I have written the initial number of moles of each reactant and divide the number of moles by the respective stoichiometric coefficient. So the coefficient of A is 1, divide this by 1. The coefficient of B is 2, divide this by 2. We have got two numbers now. Compare these two numbers. That's the only intention of doing this division. If I compare these two numbers, I'll get to know that this is a smaller value. I mean, you have to just see which is a smaller value. 4 is smaller than 5, which means B is the limiting reagent. So we are done with the box. We don't need this box again. This was used to find out who the limiting reagent is. So again, I'm repeating. After division, compare the values. 4 is smaller than 5. 4 corresponds to B, and so B is the LR. So what is this LR telling us? Which means B will be used up completely, which means A will not be used up completely. Some amount of A will be left behind, but B will be used up completely. Which means now the subsequent calculations will be based on limiting reagent. The entire purpose of finding out limiting reagent is to proceed further. That means we should know how to proceed. We should know what to do. So before that, find out the limiting reagent, because once you know who the limiting reagent is, all subsequent calculations will depend on that. So our basis is B now. Now looking at B, we'll be able to apply stoichiometry and then we'll find out how many moles of C are formed. Moles of B reacted. Moles of B reacted is equal to. Now, how many moles of B have reacted? Since B is the limiting reagent, everything has reacted, so nothing is left unreacted. So 8 moles of B have undergone complete reaction because 8 moles of B had been taken and B is the LR. Okay, so now we can find out the number of moles of C formed. So I can say moles of B reacted upon moles of C formed is equal to the ratio of the coefficients. Coefficient of B is 2 and coefficient of C is 1. Put the values here. Moles of B reacted is 8. So 8 upon moles of C formed is equal to 2 upon 1. So 8 upon x is equal to 2 upon 1. So 8 is equal to 2x on cross multiplying and x is equal to 4. What is x? So moles of C formed is x. So if I solve this further, 8 is equal to 2x and x is 4. So from this I get the value of number of moles of C formed. Right? Alright. Next question. Okay, so this is a neutralization reaction, which means an acid has reacted with a base to form salt and water. Clearly they have mentioned that acid reacted with NaOH. NaOH is a base. Right? Now, if an acid reacts with a base, I repeat, if an acid reacts with a base, safely we can use this formula. Number of MEQ of acid reacted. MEQ is milliequivalents. Is equal to number of MEQ of base reacted. The biggest advantage of using this is that we don't need a balanced chemical equation because we are using MEQ and not moles here. So for any acid-base reaction, we can use this formula. This is law of equivalence. Now MEQ is what? MEQ is millimoles into NF. See, if GQ is moles into NF, then MEQ will be millimole into NF. So millimoles of acid multiplied by NF of the acid. Millimoles of acid. So how do I get the millimoles of acid? Clearly I have been given grams of the acid. I have been given the molar mass of the acid. Grams upon molar mass is moles. Moles into 1000 is millimoles. So now I have obtained the millimoles of acid. Millimoles into NF. NF of the acid is unknown. So I'll write like this. That is what they have asked us to find. See, basicity of the acid, that means NF of the acid has been asked. MEQ of base in a similar manner. Now, we have been given the normality of the base. Normality multiplied by liters is GQ, which means normality multiplied by milliliters will be MEQ. So, normality is 0.5. Normality multiplied by milliliters is given. So, normality into milliliters is MEQ. Right? So 20 ml is the volume in ml, 0.5 is the normality. On solving this further, we'll get the value of NF. 45 upon 100. 0.45 can be written like this. Point 5 into 20 is 10, right? Right? So NF is 90 by 45, which is 2. So basicity of the acid is 2. Very interesting question. It's based on equivalent weight. Equivalent weight is also called equivalent mass. Now, We have been told that A1 grams of an element gave A2 grams of its oxide, which means A1 grams of the element combined with oxygen to form the oxide. Okay, so A1 grams of the element combines with how many grams of oxygen? If A2 is the final weight of the oxide form, that means the value of the grams of oxygen that combined with A1 grams of element will be equal to A2 minus A1. This is the main thing. We must find out the quantity of oxygen which combined with the given quantity of the element. That's what I've done. This is corresponds to, right? Don't write equal to. This means corresponds to. All right. If E is the equivalent weight of the element, then I should write E grams of the element combined with 8 grams of oxygen. This is how you define equivalent weight of an element which is forming its oxide. I repeat, E is the equivalent weight of the element. So what is E? E is the quantity in grams combined with 8 grams of oxygen. So if E is combining with 8 grams of oxygen, I will say E is the equivalent weight of the element. That's what I've done. Now, if I cross multiply, I'll get the value of E. Therefore, E into this is equal to A1 into 8. So, E is equal to 8A1 upon A2 minus A1. 8A1 upon A2 minus A1. Right? Next one, vapor density, VD. We can write VD. Vapor density of metal chloride is 77. And again we have, okay. Now see, for any element, equivalent weight has been given, right? So, now if element is M, that is the metal, let it be M. Then the formula of the metal chloride is this. Why? We know that metal will show a positive valency and chloride means Cl has a -1 valency, and from that knowledge I can write this is the formula of the metal chloride, right? Now see, equivalent weight of M, equivalent weight of M will be equal to the atomic mass, let it be X, atomic mass upon N. Equivalent weight is what? Atomic mass upon the valency. N is the valency. Now, it's given as 3. So I can say therefore, which means atomic weight of the element is 3N. X is the atomic weight of the element. That is the metal here. Now see, what is the molar mass of this entire metal chloride? I can say molar mass of this will be X into M. I mean X into 1 because here we have 1. X is the atomic weight of the metal. So X into 1 plus 35.5 N is equal to molar mass. X into 1 plus 35.5 N is equal to molar mass of the metal chloride. Molar mass is given to us indirectly. Vapor density is 77. So molar mass will be twice into 77. Twice into 77 is 154. And also X is equal to 3N. So you can write here, instead of writing X, you can write 3N. So 3N plus 35.5 N right? So basically I have now one variable with me, that is N. Okay. Now what they have asked us, what is the atomic weight? Fine. So if I get the value of N, I can multiply n by 3, I'll get x. So n is equal to 4. Okay. Okay. Now, what is x? 3n. So 3 into 4, it is 12. X is the atomic weight. 3n. 3 into 4 is 12. Next question. Similar concept. The oxide of an element. Now see, instead of metal chloride, we can talk about metal oxide as well. Metal oxide has this formula, which means if I say that this is metal oxide, that means the valency of the metal is 3, because oxide itself means O exhibits -2 oxidation state. So the formula will be M2O3 only if the valency of metal is 3, which means now atomic weight of the metal. Atomic weight of the metal is equal to what? The equivalent weight, which is 9 multiplied by the valency. Just now we use this concept, right? Equivalent weight of an element is atomic weight upon valency. So atomic weight will be equivalent weight multiplied by valency. Now, what is the molecular mass of the oxide? So now it's simple. Molecular mass of the oxide will be what? 2 into atomic mass, that is 27, plus 3 into 16, this is 48 plus 54. Molecular weight, so I have to represent U. This is in U, and molar mass is in gram per mole. The values are same. So if they ask me what is the molar mass, I'll say 102 gram per mole. If they ask me what is the molecular mass, I'll say 102 U. C option. All right. Next one. Very easy. Different proportions of oxygen in the various oxides of nitrogen proves the law of. Okay. See, to make it easier, let's say I have some oxides of nitrogen. I'm writing a few oxides of nitrogen. Okay, I'm writing a few oxides of nitrogen. These are various oxides of nitrogen. When we see that there are two elements and both the elements are present in all the compounds, that means it is law of multiple proportions. That's all. Law of multiple proportions, because there are nitrogen, oxygen in every oxide. So the elements are same everywhere, but the formulae are different, which means this is law of multiple proportions. Next question. For 1 liter flasks. Now they have given us 4 flasks having the same volume, because every flask has a volume of 1 liter. So the volume is constant for all. Next, we have 4 different gases. Okay, hydrogen, that is H2. Remember, when they say hydrogen, it's by default H2. Don't write H, because hydrogen is diatomic. Helium is inert gas, He. All inert gases are monoatomic. Oxygen is again diatomic, so I must write O2. I'm not supposed to write O. Ozone is O3. It's a triatomic gas. Okay. The main part is this: same temperature and same pressure, which means all the gases are at the same temperature, they are at the same pressure, and also all of them occupy the same volume, because the flask has same volume for all. Okay, now the ratio of total number of atoms of these gases present in the different flasks would be, all right. So this is an application of Avogadro's law. So the concept is equal volumes of all gases, irrespective of the nature of the gas, will contain equal number of molecules if temperature and pressure are constant. I mean, if all the gases are at the same temperature and at the same pressure. So same temperature, same pressure, same volume. So directly it's an application of Avogadro's law, which means the number of molecules is equal. So let the number of molecules be equal to X. The number of molecules is X, right? Now the number of molecules is same for all these four gases. We know that number of atoms is equal to number of molecules multiplied by atomicity. Atomicity of hydrogen is 2. It's a diatomic substance. Atomicity of helium is 1. Atomicity of oxygen is 2. Atomicity of ozone is 3. So number of atoms is 2x for hydrogen, 1x for helium, 2x for oxygen, and 3x for ozone. So ratio is what? 2x is 2, 1x is 2, 2x is 2, 3x. X will get cancelled. So the answer is 2 is to 1 is to 2 is to 3. The option. A chemical equation is balanced according to the law of conservation of mass, obviously, because we cannot violate law of conservation of mass, which means the total grams, if I'm talking about grams, I mean if I'm taking everything in grams, then the total grams of all the reactants reacted is equal to the total grams of all the products formed, and that is why we balance chemical equations. So it's law of conservation of mass. All right, let's come to redox reactions. A few simple questions we'll discuss. See, now before starting with the questions, again I would like to tell you a very important thing. You all should take care of that. The point is, before attempting to solve any question related to redox, ensure that you are thorough with oxidation states of the elements. The most common oxidation states you should know. So like for oxygen, for hydrogen, right? And we all know that for elements belonging to group 1, plus 1 is the only oxidation state in combined form, that is when they are not in their elemental form. And similarly, for any element of group 2, plus 2 is the oxidation state. Again, if it is not in the if it is in the combined form, that means if it is not in the elemental form, because if anything is in the elemental form, then the oxidation state is 0. Okay, one more thing is for fluorine, because fluorine is the most electronegative element. If fluorine is again in combined form, the oxidation state of fluorine is -1. So you must be thorough with fluorine and elements of group 1 and elements of group 2. And obviously hydrogen and oxygen. If hydrogen is bonded to a non-metal, the oxidation state of hydrogen is +1. And if hydrogen atom is bonded to a metal, then the oxidation state of hydrogen is -1. So all these things we must be aware of, and then only we will be able to find out the oxidation states of the other elements. Okay, so in this question they have asked us, okay, now see, KMNO4 is potassium permanganate. KMNO4 is very common in questions of redox reactions, and also K2Cr2O7 is very common. KMNO4 is potassium permanganate, and we all must remember that MnO4 minus gets converted to Mn2 plus in acidic medium. MnO4 minus gets converted to MnO4 2 minus in strongly basic medium. Strongly basic. And MnO4 minus gets converted to MnO2 in weakly basic medium or neutral medium. So this is for weakly basic or neutral. Now in the question, weak alkaline, that means the third one, so MnO2. Okay, again acidic medium. So KMnO4, so straight away we will write Mn2 plus. Just now we discussed that MnO4 minus gets converted to Mn2 plus in acidic medium. This is colorless, this is purple. Lowest oxidation state of phosphorus is in. So there are 4 compounds of phosphorus given to us. We have to find out the oxidation state of phosphorus in each of these 4, and then finally see in which of the following compounds phosphorus exhibits lowest oxidation state. So For this, let it be X for phosphorus, oxygen minus 2, H plus 1. As I said, hydrogen shows oxidation state of plus 1 if H is bonded to a non-metal. All of these are non-metals in all the options. So safely we can say that hydrogen shows plus 1 as its oxidation state. So plus 1 into 3 will be plus 3. Then X minus 2 into 2 will be minus 4. Overall, it is neutral, so equal to 0. From here, X will be equal to plus 1. Likewise for this, likewise for this, likewise for this. Right? So again 3 plus X, 4 into minus 2 is 8 is equal to 0. For this again, so 4 plus 2x minus 14 is equal to 0. And for this, the lowest is plus 1. H3PO2 is called hypophosphorus acid. You should know the name. Next. Okay. Hot concentrate sulfuric acid is a moderately strong oxidizing agent. Okay. Which of the following reactions does not show oxidizing behavior? It does not does show. So be careful. Does not show oxidizing behavior. Now see, if we have an acid-base reaction, it can never be redox. Keep this point in mind so that you don't have to check the oxidation states of the elements involved. Straight away we can memorize any acid-base reaction is never redox, which means there is no oxidation, there is no reduction. Similarly, any double displacement reaction is never redox. Okay, so if I talk about the second reaction, that is this reaction, it is a double displacement reaction. See, CaSO4HF. So double displacement reactions are never redox, and if there is no species getting oxidized or reduced, there is no oxidizing agent, there is no reducing agent. So obviously H2SO4 does not act as an oxidizing agent in the second one. That's what they've asked. Does not. Next one. The correct coefficients. Okay, very simple. Now see, we have to balance this reaction. H plus means it's acidic medium. So simple way to balance is using the N factor. Let's find out the N factor of this. Oxidation state of manganese is plus 7. Here it's plus 2. So N factor of MnO4 is, MnO4 minus is 2 minus 7 into 1 and then modulus. So 5. N factor of C2O4 2 minus. N factor of C2O4 2 minus is what? 4 minus 3 into 2. So 2. So we have found out the N factor. So I can write like this. 2 MnO4 minus. After finding out the N factors, we will write this. Now, what is the method of balancing this reaction? If N factor of MnO4 minus is 5, I will place 5 in front of C2O4 2 minus. And if N factor of C2O4 minus, 2 minus is 2, I will place 2 in front of MnO4 minus. So I just do exchange. So 2 MnO4 minus plus 5 C2O4 2 minus gives us Mn2 plus CO2. Now balance those elements which underwent change in oxidation state. So manganese, so here we have 2 carbon atoms need to be balanced, so 10 CO2. Finally, we will balance oxygen atoms and then we'll balance hydrogen atoms. So oxygen atoms need to be balanced now. In acidic medium, check which side is having deficiency of oxygen. So here I have 20 oxygen atoms. Here I have 28 oxygen atoms. So deficiency is here, and hence here I will add 8 H2O. So this side is deficient, and so to this side I added 8 H2O. And finally, I'll now balance this reaction by balancing hydrogen atoms. Medium is acidic. I will add H plus ions to the side which is having a deficiency of hydrogen atoms. This side had deficiency of hydrogen atoms, and hence I added 16 H plus ions to the left hand side. Now it is a balanced chemical equation. So The coefficients of MnO4 minus C2O4 2 minus 1H plus are 2, 5 and 16 respectively. So option B. Okay. So it's a redox reaction because KMnO4 is involved. So simply I will write KMnO4 is reacting with FeSO4. Now see, whenever FeSO4 is involved, you simply write Fe2 plus because SO4 2 minus does not get oxidized. So Fe2 plus is the active component that's taking part, so it is getting oxidized. Okay, now I will write Fe3 plus because Fe2 plus gets oxidized to Fe3 plus. Fe2 plus gets oxidized to Fe3 plus, and after that, since the medium is acidic, straight away I can write Mn2 plus is definitely formed, and from here we can proceed. So for any redox reaction, we can simply write MEQ, or rather GEQ also you can write whatever it is. So GEQ of MnO4 minus is equal to GEQ of Fe2 plus. GEQ of oxidizing agent is MnO4 minus and reducing agent is Fe2 plus. GEQ is a moles into NF, right? Moles into NF. Now, moles is what? Moles is molarity into liters. Already we have discussed. So molarity is this. Liters, let it be V. So molarity into liters into N factor 2 minus 7, that is 5. Similarly, GQ of Fe2 plus. GQ is what? Moles into NF. What is moles? Moles will be grams by molar mass. From 2 grams of FeSO4, we'll have 2 grams of Fe2 plus. Right? And FeSO4. How many moles of FeSO4 are there? 2 upon molar mass of FeSO4. The number of moles of Fe2 plus will be exactly same as the number of moles of FeSO4. So the number of moles of Fe2 plus will be 2 upon molar mass of FeSO4. So what is the molar mass of FeSO4? 56 plus 96. 152. So 2 upon 152. This is the number of moles of FeSO4. Also, this is the number of moles of Fe2 plus. NF. What is NF? Oxidation states need to be checked. 3 and 2. So subtraction, if I do 3 minus 2, 1. And here also it's 1. So 3 minus 2 into 1. So this is the only unknown parameter. On solving this, I'll get the value of V. So this is the value of V. Right? So law of equivalence has been used here. So what is the conclusion? The conclusion is whether it is an acid-base reaction or a redox reaction, we can use law of equivalence easily without hesitation, and we don't need to balance the equation. Simply use GQ or MEQ. So here I have used GQ of MnO4 minus is equal to GQ of Fe2 plus. For acid-base reaction, I will write GQ of acid is equal to GQ of base reacted. Okay. So I hope you have been able to follow whatever we discussed, right? So all the best. Keep practicing. Physical chemistry requires a lot of practice. Use pen and paper. Don't practice orally. Okay. Thank you.